Measuring plant biomass using double sampling methods. The measurement methods that are most commonly used to measure plant biomass on rangelands are harvesting, estimation, double sampling, and indirect methods. In this lesson, we're going to focus on learning how double sampling is used to estimate plant biomass. Double sampling is a sampling approach that is used for variables that are either time-consuming or difficult to measure, but they have the quality that they are highly correlated to another variable that is easier to measure. The principle behind double sampling is that we frequently estimate and infrequently measure. The advantages of double sampling for measuring plant biomass is that we can increase the efficiency of our sampling effort by frequently estimating biomass, but we retain the accuracy of the harvesting method. Disadvantages are some slightly more difficult calculations using regression analysis. So let's take a look at an example of how this would work. We see in this diagram here 25 quadrats that were all estimated. The numbers in the quadrats represent the number of grams of herbaceous material that were estimated in the quadrats. After they were estimated, a subset were also harvested. So we have double sampling in those quadrats that were both estimated and harvested and weighed. So let's see how the analysis works by looking at an Excel spreadsheet that has the information that we need in it from this sampling effort. We can see in column B the values that were estimated in all 25 quadrats. In column C, we see the values that were harvested and weighed. What we need to do is develop a regression equation that describes the relationship between the harvested and the estimated values. And we can do that easily using Excel. If we go to the Insert tab and request a scatter graph, what this is going to do is graph those 5 points that were both estimated and harvested. Now we need the regression equation, so if you go up to Layout and request a trend line, we don't want to go with the default, so we're going to ask for more trend line options, and we want to display the regression equation on the chart and also the R² value on the chart. We do not want to set the intercept to 0. Okay, having done that, it's now displayed on the chart. We can see the regression equation written in the form of y equals mx plus b. The regression equation provides information about the relationship between the dependent and independent variable. The dependent variable in this case is the harvested or the actual values, and the independent variable are the estimated values. The regression equation provides information about how much of the variation in the dependent variable can be explained by the independent variable, which is on the x-axis. The R² value is the coefficient of determination, and that provides information about the strength of the relationship. As we can see here, we have a pretty good linear relationship between these 5 points. It's not perfect. If it was, we would have an R² of 1.0. and all of the points would fall perfectly on the line. But we're going to use this information to adjust the values of the estimated quadrats. So I'm going to copy that equation over here, and I'm going to clean it up a little bit because the Excel syntax does not want that y in the equation. And I'm going to set it up so that I'm going to replace x in the equation with the value for the estimated amount that came from that quadrat. And by doing that, I now have an adjusted fresh weight value. I'm going to copy the equation and paste down so that it's going to be applied for all of the observations in the 25 quadrats. Now, we do need to adjust for dry weight, and the biomass was weighed in the field. It was also taken back to the lab, dried, and we have an estimated dry weight value of 84%. So I'm going to show you how to adjust for that. Again, we're going to put in an equation. We want to say equals 0.84 times the value of the adjusted fresh weight. Okay, having done that, I'm going to copy the equation and paste it for all of the observed quadrats. The last thing that we want to do is convert our biomass estimate from the adjusted dry weight on a grams per quadrat basis to a kilogram per hectare basis. And in order to do that, these quadrats were 1 meter squared, and so all we have to do is multiply the amount of the adjusted dry weight by 10, and that will convert grams per meter squared quadrat to kilograms per hectare. And so if we do that, again, copying and pasting for all of the quadrats, we now have an estimate of kilograms per hectare based on each one of these quadrats. Now, we would never report all 25. What we need is an average value, and we can get that very easily by asking for an average of these points here, and it's multiplied it out, so our average value on a kilogram per hectare basis is 228 kilograms per hectare. Okay, so coming back here now, if we look at what this resulted in from double sampling, we can see that based on those 25 quadrats that we estimated and the 5 quadrats that we harvested, we have an estimated biomass of 22.8 grams per quadrat, or 228 kilograms per hectare. And we were able to determine this by using regression analysis. Comparative yield is an alternative approach to using a double sampling approach that involves ranking. It involves a set of 5 reference quadrats that are established at the site where we're doing our sampling. And usually we start out by establishing the first 3, number 1, number 3, and number 5. Number 3 is established in an area that has about a moderate amount of vegetation for the site. number 1 is established showing with biomass that is a relatively low amount, not absolutely the lowest amount, but a low amount. And number 5 is established in an area over plants that are displaying a fairly large amount of biomass for the site. We then subsequently identify a quadrat number 2 and a reference quadrat number 4. In doing this, we now have 5 reference quadrats. Usually this is an iterative process where you establish your reference quadrats and then you have to clip them to make sure that you are doing a good job of estimating the amount of material that's in each quadrat. If you've clipped them, that means that you have to go back and reestablish them. But eventually you end up with a set of 5 reference quadrats that you leave in the field while you are doing your estimation using the comparative yield method. So here we see the reminder of what these 5 quadrats looked like, and they can be scattered around, usually fairly close to each other, so that we can refer to them as we are estimating quadrats in the field. And what we do is, instead of estimating the number of grams, we estimate the rank or the reference quadrat that is represented by each one of the quadrats. So this quadrat resembled number 1. This quadrat was midway between a number 1 and a number 2 reference quadrat, so it was given a mid-rank of 1.5, and that's perfectly acceptable to do that. We then clip our reference quadrats and determine how many grams there are in each one of the quadrats. We also select a subset of the quadrats that were estimated and harvest those as well. And we use this information using a regression analysis that's very similar to the one that we just looked at, and essentially come up with a mean rank for all 25 of the quadrats that were ranked using comparative yield, and then using the information that we have about how much biomass is associated with that rank, we can come up with an estimate of the total biomass of all species combined. Remember, when we're doing comparative yield, we're not separating by species, but we're ranking all of the vegetation in each one of the quadrats. In this case, the estimate on a kilogram per hectare basis was 1,235 kilograms of biomass per hectare. Now we can combine this with the dry weight rank method. Dry weight rank estimates species composition on a biomass basis. In this method, within each quadrat, we rank the species, the 3 species, with the highest amount of biomass. So it considers all of the species in a quadrat, and you rank the top 3. Even if there's 12 species in the quadrat, you still only rank the top 3. It assumes that there are going to be 3 ranks assigned, and so if you do have a quadrat that only has 1 or 2 species, you can assign multiple ranks. So let's see how this works. Here we see a very simple scenario of 3 quadrats, and there's only 4 species in this community. There's a purple flower, a yellow flower, a white flower, and a grass. We examine the first quadrat and rank the species based on the amount of biomass. For this example, we're going to use size or cover as a proxy for biomass, but we would be doing this in the field using real biomass because we're right there with the plants. So in this first quadrat, we would assign the grass the number 1 rank, the white flower the number 2 rank, and then the purple flower the number 3, because there's more of it than there is of the yellow dandelion. In the second quadrat, we would assign ranks of 1 to the yellow dandelion, 2 to the white flower, and 3 to the grass. In the third quadrat, there's only 2 species, so we have to assign multiple ranks. We decided that the grass has the most biomass, so it automatically gets number 1, and there's quite a bit of biomass of the yellow dandelion, so it gets both a 2 and a 3. You could have other combinations where the grass could get ranked 1 and 2 and the dandelion could get ranked 3, etc. But they do have to be distributed among the 2 species that are in the quadrat. If there was only 1 species, it would get all 3 ranks, 1, 2, and 3. So let's take a look at how this plays out when we do the analysis. First, we summarize the ranks. The purple flower was not ranked 1 or 2, but it was ranked number 3 once. Dandelion was ranked a number 1, a number 2, and a number 3 one time, and the white flower was ranked number 2 twice. The grass was ranked number 1, it was ranked the first ranking twice, and it was given the third ranking once. So we're then going to weight them. The first rank gets weighted 70% or multiplied by 70. The second rank is weighted by 20%, and the third rank is weighted with 10%. We then sum these weights, so the purple flower has 10. If you add 70, 20, and 10, that equals 100, etc. We know that we've done this correctly because we have 3 quadrats that have to have 100% composition, so 100% times 3 equals 300, and if you add 10, 100, 40, and 150, that equals 300. We then calculate a species composition based on this by dividing the weighted sum by the total amount, which is 300%. And so we get 3.3% is what the contribution of the purple flower, but 50% is the contribution of the grass to the total species composition in this very simple community. Now we can use the dry weight rank information with the comparative yield information. Remember, we had an estimate of 1,235 kilograms per hectare from the comparative yield. So if we multiply that amount by the species composition, then that means that we had 41 kilograms per hectare of the purple flower, 411 kilograms per hectare of the yellow flower, etc. This is a very rapid way of being able to combine species composition data and that we get from the dry weight rank with the total biomass estimate that we get from comparative yield. So to summarize, by using double sampling methods in which we both estimate and harvest, we estimate frequently and we harvest infrequently, we can develop regression equations to efficiently estimate the biomass on a site. Double sampling can be done by a simple estimation and harvest approach that we saw first, or it can also be done using a combination of comparative yield, and dry weight rank methods.